begin by discussing the simplest learning problem, which is that of estimating a set of parameters. And the key building block for parameter estimation is what's called maximum likelihood estimation. So we're first going to define that and then build on that in the context of more interesting problems. So let's go back to the simplest possible learning problem, where we are generating data from a biased coin, which is a Bernoulli distribution, and the probability that x takes the value 1 is defined by some parameter theta, and the probability that it takes the value 0 is therefore 1 minus theta. And let's imagine that we're given access to a data set D, which is a bunch of instances, x1 up to xm, that are sampled IID from the distribution P. So let's remind ourselves what it means for what the IID means. So first, the first I means that the tosses are independent of each other. And the ID means that they're identically distributed, which means that they're all sampled from P. And our goal is to take D and reconstruct theta. So let's think about this as a probabilistic graphical model. And in fact, it's a probabilistic graphical model that we've seen before when we first talked about plate models. So here we have a parameter theta and a bunch of replicates of the same experiment, which are these x's over here. Which are sampled from theta independently. And we can see that if you think about this as a graphical model, as written over here, we can see that each xi depends on theta, and that they're conditionally independent of each other once theta is known. So they're independent and identically distributed given theta. And if you think about this as a graphical model, well, it better have CPDs. And so the CPD for the mth toss given theta is that the x takes the value x1 with probability theta, and the value x0 with probability 1 minus theta. And that's a completely legitimate CPD. It's a CPD whose parent is the value theta, which is the parent of the x variable. It's a continuous variable, but we've done those before. So now that we've specified this as a probabilistic graphical model, we can go back and think about how maximum likelihood estimation would work. And so the goal is to find the parameter theta, which is in the interval 0, 1, that predicts D well. So the quality of a particular parameter theta is how well it predicts D, which can also be viewed as how plausible is D given a particular value of theta. So let's try and understand what that means. We can ask, what is the probability of the D that we saw given a particular value of theta? And since the tosses or the instantiations xi are conditionally independent given theta, we can write this as a product over all of the m instances of the probability of the mth instance given theta. And so now let's think about what that is in the context of a concrete example. Let's assume that we have tossed this coin 5 times and we have 3 heads and 2 tails, or 3 ones and 2 zeros. So if we actually write down what this probability function looks like, we can see that that's going to be the probability of getting heads given theta times the probability of getting tails given theta times the probability of the second tail times the probability of heads times another probability of heads. And the probability of the first head given theta is theta times 1 minus theta for the tail, 1 minus theta, 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 or theta to the power of 3, 1 minus theta to the power of 2. And that is exactly the function that's drawn over here. Now, if we're looking for the theta that predicts D well, we just defined that as the theta that maximizes this function. And if we draw a line from this maximum down to the bottom, we can see that this function is maximized at the point 0.6, which, not surprisingly, is the same as the 3 heads that we saw over the 5 total tosses. So generalizing that, let's assume that we have observed in this context MH heads and MT tails, and we want to find the theta that maximizes the likelihood. And just as in the simple example that we had, this likelihood function is going to have theta appearing MH times and 1 minus theta appearing MT times. And so that's going to give us a likelihood function that looks just like the likelihood function that we saw on the previous slide. And if we think about how we can go about maximizing such a function, then usually we take the following steps. First, it's convenient to think about not the likelihood, but rather what's called the log likelihood, denoted by a small l, which is simply the log of this expression over here. And that has the benefits of turning a product into a summation. And now that so that gives us a simpler optimization objective, but one that has the exact same maximum. And we can now go ahead and do the standard way of maximizing a function like this, which is differentiating the log likelihood and solving for theta. And that's going to give us an optimum, which is exactly as we would expect. That is, it's the fraction of heads among the total number of coin tosses. And that's the maximum of this log likelihood function, and therefore of the likelihood as well. Now, an important notion in the context of maximum likelihood estimation that's also important when we develop it further is the notion of a sufficient statistic. So when we computed theta in the coin toss example, we defined the likelihood function as an expression that has this form. And notice that this expression didn't care about the order in which the heads and the tails came up. It only cared about the number of heads and the number of tails, and that was sufficient in order to define the likelihood function, and therefore sufficient for maximizing the likelihood function. And so in this case, MH and MT are what's known as sufficient statistics for this particular estimation problem, because they suffice in order to understand the likelihood function and therefore to optimize it. But more generally, a function of a data set is a sufficient statistic if it's a function from instances to some vector in Rk, if it has the following property, if this function s of d has the following property. For any two data sets, d and d prime, and any possible parameter theta, we have that the following is true. If s of d is equal to s of d prime, then the likelihood function for those two data sets is the same. So what's s of d? S of d is the sum of the sufficient statistics for all of the instances in D. So let's make this a little bit more crisp. What we're trying to do is we're trying to look at a bunch of data sets, for example, all sequences of coin tosses, and we're trying to summarize data sets using a smaller, more compact notion, which is statistics, that throw out aspects of the data that are not necessary for reconstructing its likelihood function. So let's look at the multinomial example, which is the generalization of the Bernoulli example that we had before. So assume that what we have is a set of measurements of a variable x that takes on k possible values. Then in this case, the sufficient statistics, just like before, whereas before we had the number of heads and the number of tails, here we have the number of values, the number of times that each of the k values came up. So we have m1, m2, up to mk. So for example, if you're looking for a sufficient for sufficient statistics for a 6-sided die, you're going to have M1 up to M6, representing the number of times that the die came up 1, up to the number of times that it came up 2, 3, 4, 5, and 6. And so what is the sufficient statistic function in this case? It's, remember, it's a tuple of dimension k, which are the different numbers of values, which are the number of different values of the variable. And the sufficient statistic for the value xi is one where we have a 1 only in the ith position and 0 everywhere else. So if we sum up S of xm over all instances in our data set, you're going to get a vector where you only get a 1 contribution when the mth data instance comes up that particular value, and so that's going to be M1, M2, and M3. And this is a sufficient statistic because the likelihood function can then be reconstructed as a product of theta I mi, where this theta I here is the parameter for x equals x little xi. Let's look at a different example. Let's look at the sufficient statistic for a Gaussian distribution. So as a reminder, this is a one-dimensional Gaussian distribution that has 2 parameters, mu, which is the mean, and sigma squared, which is the variance, and that can be written as in the following form, which is one that we've seen before. And we can rewrite the exponent in the following way. We can basically blow out the quadratic term in the exponent, and you end up with a likelihood function that has minus x squared times a term plus x times the term minus a constant term. And the sufficient statistics for a Gaussian can now be seen to be x squared, x, and 1. Because when we multiply p of x for multiple occurrences of x, we're going to end up adding up the x squared for the different data cases, adding up the x's for the different data cases, and then this is just going to be the number of data cases. So the S of a data set D is going to be the sum over m x of m squared, the sum over m x of m, and just m itself. And from that, we can reconstruct the likelihood function. How do we now perform maximum likelihood estimation? So as we talked about, we want to choose theta so as to maximize the likelihood function. And if we just go ahead and optimize the functions that we've seen on previous slides, for multinomial, that maximum likelihood estimation turns out to be simply the fraction. So for the value xi, it's going to be the fraction of xi in the data, which again is a perfectly very natural estimation to use. For a Gaussian, we end up with the following as the maximum likelihood estimates. The mean is the empirical mean in the distribution. That is the average over all of the data cases, and the standard deviation is the empirical standard deviation. So to summarize, maximum likelihood estimation is a very simple principle for selecting among a set of parameters given a data set D. We can compute that maximum likelihood estimation by summarizing a data set in terms of sufficient statistics, which are typically considerably more concise than the original data set D, and so that provides us with a computationally efficient way of summarizing a data set so as to do the estimation. And it turns out that for many parametric distributions that we care about, the maximum likelihood estimation has an easy to compute closed form solution given the sufficient statistics.